Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
So the last topic was to build a demand paging using which we can implement the virtual memory space. Okay, so in that we just discussed what is the basic idea, right? You don't have to swap the entire process onto the memory. You can swap only what is required. So we call such a swapper by the name lazy swapper. Okay, so the idea here, first we'll write a diagram of the whole process, how the main memory will contain the part of the program, right, by using a specific function called swap out. So you can take out the program which is not required and you can put it into the memory. And the second option is to call a function called swap in, right, where a particular program or a process will be loaded onto the main memory. Okay, so that is, let's draw a small diagram. Let's say this is the main memory of the computer, and let us say we have memory of the physical memory of the computer. Actual memory is represented in this fashion. Okay, so we know that the memory of our computer is divided into several parts. Let's consider some of the parts. Okay, in one portion of my main memory I have this region. This region corresponds to, maybe it's inside the RAM, or the one location from where the computer is executing the functions. Okay, so out of this, let me highlight, say, two portions of this. Let's say this is one portion of the memory, main memory. Let's say I'm taking four such locations, and let's take another location which consists of, say, these three locations. What exactly is happening here? Let me call the first part as, right, the program A. Okay, this is corresponds to a particular program or a process by its, let's say its name is A, and we have another program or a process whose name is, say, it's B, process B. Right, now this particular process, we know that our computer's memory has been designed, right, through, maybe you can use the switch capacitors over there. Capacitors will store the data in the form of 1 or 0, right, binary data, right? Anything has to be represented in binary form in order to make the computer to store it or understand. So we can have capacitors, BJT, FET, right, irrespective of whatever it is. You have memory organized in the form of cells. Okay, let me consider few of the cells, right, only few cells I write here. Okay, now what happens, when this particular code or the process A is running, and once it is done, or once the programmer has written something, right, once the usage is over, you can write them onto the cells by a specific process called as, this is swap out. You are writing the function to the cells. At the same time, there is another option. The second option is, now these values we are trying to load from the computers to the memory from the cells where we have saved it, right? You are trying to load this, so you see the direction, it is incoming, right? You are trying to write something into this, so this is called as the swap in. So swap in is first thing, one option. Swap out is the other option, right? So previously we discussed about a lazy swapper, right? Lazy swapper was instead of loading the entire process into the memory, right, you can use the part by part by using the lazy swapper. Okay, now a lazy swapper never swaps a page into the memory unless that page is needed. This is still here we had discussed. Now this is the diagram corresponding to that. All right, so now we are viewing a process as a sequence of several pages. This one page can be of 4 cells, 10 cells, 15 cells, any size. So size doesn't matter here. That's why we are showing different sizes of process or the programs A and B. They are different because you can swap out different amount of page and swap in different amount of page. So because of that reason, we are considering the process as a sequence of pages. So rather than as one very large address page, right, instead of considering the memory required for that particular process as a very big continuous address page, now the swapper is technically, right, I may not be able to use the swapper uh, as it is, because the word swapper says that you are swapping the what you call the whole memory at once. But swapper is, right now what swapping operation we are discussing here is not exactly swapping. It actually selects a part of the whole code, and right, we will replace it with the main memory. Okay, so because of that reason, now we'll change the name into the pager. So instead of swapping, uh, swapping idea says that you are actually copying the entire content, but right now we are not doing that. We are doing part by part, right? So individual pages are going to be moved into the memory or moved out of the memory. So in this context, what we are discussing is, right, we view the process, we view any process, we view a process as a sequence of pages. Okay, so it's not like a computer, the continuous computer memory. It's like page by page, right? It can contain few cells or hundreds of cells, doesn't matter. You call it as a page by page, right? Whatever is required, you copy, right? So what we do, pages, uh, the entire process is done by, so you have this term which is coming up now onwards regularly called pager, pager, right? Pager is going to deal with the individual pages of a process. So we don't call it as a swapper now, we will call it by the name the pager, because right, whenever a page is demanded, right, the pager will do the required job. So now when the process has to be swapped in, right, pager will guess. Initially there will be a guessing operation, because there are some very standard definitions associated with a uh, paging operation, right? So if it is something like a controlling operation, then this is the required number. If it is related to IO operation, then this could be the ideal size. So depending on that logic, uh, the pager will do a guessing. That's the initial step. So it will perform a guess what is used. Maybe it has learned something from the previous processes which it has swapped, and now it wants to swap the similar uh, context once again. Then it will have an idea that okay, this is the required number of pages. So instead of swapping that whole process, pager will bring only the necessary pages into the memory. So how it begins, right? So the pager works in the following fashion, right? So when a okay, we can write when a process has to be swapped, whenever it has to be swapped, the pager initially makes a guess. Okay, G2SSES, it will guess, right, which pages are to be or I can write yeah, are to be used. Okay, and once it will do a guess, right, and the pager brings necessary pages into the memory. Alright, so it avoids reading into the memory pages that will not be used. Okay, so total required swap time is also reduced, physical memory is also reduced, all these things will happen. Anyway, we know that already. Now, using this scheme, now we need some specific hardware to distinguish the pages that are in the memory and the page that are actually present on the disk, right? So disk already has been shown in a cylindrical format, which can be the hard disk, right? Programs will not run from hard disk. Program will run from your main memory, can be RAM or inside the CPU registers, etc. So now we need a hardware to identify that which part of your code is in the main memory that's it's running and which part of your code is actually present on the hard disk, right? We need to distinguish that. So we need a specific hardware to support this. Without that, it is impossible. So sorry. So let us write that point now. Uh, therefore, therefore, we need a specialized hardware support, right, to distinguish between two things. First one is the pages, uh, yeah, pages that are not present in the memory, that are not in the memory, like RAM, and the pages that are on the disk. Okay, so the valid and invalid bit scheme will be used for this, right? Again, that just remember this name. Something you will call it as a valid, something you call it as invalid. So valid and invalid are the concepts used. You use some bits, like you can put a 0 over there to make it invalid, or just you can put a 1 over there to make it valid. So this concept is actually taken from the previous chapter, right? So I'll just try to explain that in a quick fashion next in an image using a diagram later. But just remember, there is what is called as a valid invalid bit scheme can be used for this particular purpose. So we'll write, so valid invalid, uh, there is a scheme associated with that. Okay, so I call it as bit scheme can be used for this purpose. So our we have to distinguish between, right, which is present in the main memory, which is present on the hard disk. So two things to be separated, right? We use with the data itself, you use a separate bit dedicated for identifying valid or invalid, right? So validity could be something like, okay, it is present in the memory. Invalid is something like, it's not present in this memory, it's present in the hard disk. Like that we can use it. So what exactly we are using, right? We are trying to use the valid and invalid concepts as per the following points. Say, so valid means what we'll write. So when we say that a particular data is valid, or whenever you use the bit and you fill the bit value as valid, okay, so this means the associated page is, you can say, is both, it's legal and it is in the memory. All right, and so if you say a particular page file is valid, then that means it is in the memory and it is legal. Okay, at the same time, if we try to call a particular page is invalid, so corresponding to the invalid bit, the page is either not a valid page, okay, or it is valid but currently it is present on the disk. So both can be mentioned by using a same bit, that is invalid bit. Okay, I'll write both of them. So either the page is invalid, this is the first point. So when we say invalid, right, not in the logical address of the process. So I'll just write the meaning of this. So this means not present in the logical address of the process, right? So this means it is a invalid data, which means you have given some address, but that particular address contains nothing, right? You don't have a data present over there, which means it is invalid data. So that's the first point. I'll write an or. Okay, that is first type of invalidity. Now we'll go for the invalidity in a different way. In this case, right, uh, the data is valid, or the page is valid, but is currently on the disk, but is currently located on the disk, not present in the main memory, it is present on the hard disk, right? So you see that valid and invalid bit can be used to identify where is this particular process and where is the code. So you read a code from, right, to virtual memory, and in the virtual memory, by just looking at a specific bit, it can be identified that yes, it is present on the disk or it is present in the main memory or RAM or registers or wherever we can identify. Okay, now we will be using a page table entry for a given page, right? That is brought into the memory, right? By just looking at that page table entry page, which is presently in the which is present in the memory, which is not present in the memory, right? Can be identified, right? Using a very simple technique. Okay, we'll discuss about that technique now. So that technique is called as a page table technique. So we'll write the page correspond, we will make a big table which contains the page and the details of the page in the form of a table. So the page table entry for a page, for any given page uh, that is brought into the memory is a set, right? It will be a set uh, with valid tag. There will be a valid tag associated with that particular memory which is brought into the memory. If it is present in the memory, you will be having a valid tag, so you will say that it is valid. If it is not present, right, in the memory, right, you will actually mark it as invalid. Okay, I'll continue here itself. And the one the one which is not in memory, it will be marked as invalid. Okay, and it contains the address of the page on the disk. So you have two things that can be present. I'll write an or here. So or that particular location can contain, or contains, in the sense the page table will contain what? The address of that particular page on the hard disk. Contains the address of that particular page on hard disk. So using this, right, we will be able to distinguish whether the page is present and whether the page is not present. So we will be looking at this concept by using a diagram, right? And we'll write some pages are not in memory, some pages are present in memory. So we have to distinguish that with the help of a diagram. Okay, so next we'll look at the diagram. So this is the example. So I'll write an example of a page table. Example of a page table. This is directly taken from the previous chapter. Okay, let's write that. So okay, so let us consider that there is a logical memory. So first part of the diagram will be a logical memory. So this is the logical memory. Corresponding to a logical memory, I can have what is called as a page table. Let me write a page table over here. Okay, fine. This is a page table. Then you need to use the actual, that is a physical memory for representation. This is where the data is present, and for a pictorial representation I need what is called as the physical memory in the form of a disk. Okay, so let's write the disk over here. Okay, so this is the part of this, which is the disk. All right, now okay, so let us say we have say 8 locations in the logical space. 1, 2, 3, 4. All right, and we know that this logical space, whatever we write, is going to have some continuous, right, locations. So I'll write this is logical memory. So corresponding to what should be the address? Address should be continuous. So I'll write 0, 1, 2, 3, 4, 5, 6, 7. So totally 8 locations in the logical memory. So they contain the address of actual data, right? So maybe the data present here is A, B, D, E, F, G, and H. All right. Now, corresponding to them, we have very similar properties to be represented in the form of a table. So that is what is called as a page table. So let me write the page table now. So this is the page table. Okay, so starting from okay, I need another value here, that is the bit associated with the valid or invalid. Okay, so now this is the page table where I'm writing the valid or invalid bit over here, right? Let's say this is valid. Okay, first let me give the addressing here: 0, 1, 2, 3, 4, 5, 6, 7. So this is called as the page table. Now let us assume that out of the data that is present in the logical memory, right, some part of code is not present in the main memory, and that is present on the hard disk. Okay, so I just have to show that, okay, these are the values, they are not present in the memory. Whatever is present in the memory I can actually show now. So the page table is valid when something is present. Okay, so for example, say this is present, so fourth one is corresponding to maybe E. Okay, E is present, and maybe another number I can write, maybe the sixth one, right? In this I'll write 6 and say this is valid. Let's say that there is actually I have shown only 8 values, but there is 8, 1, 9th, 10th, and so on. It's present in that way. Okay, so that particular number, maybe I know that this is say ninth one, that's also valid. They are actually present in the main memory. Whatever is not present here, right, you will just write I over there, indicating that this is invalid. But this could be a 0 and 1. Okay, 1 for valid, 0 for invalid, right? Any technique can be used here, but just to identify the specific idea about validity and invalidity, we are writing I and B in this case. So let's write this. So this particular bit, what you write here, is corresponding to the valid or invalid bit. Okay, now we can trace this out using the following technique. Now let's, sorry, 9, this value 9, 9 is actually present on the logical memory, we have not shown. Okay, 9 means here, see, in this particular point you see that the address will grow like 9, 10, 11. So the ninth one, whatever is there, that's what we are trying to represent here. Okay, so we have shown logical memory only till 7, 0 to 7, but 9 corresponds to something which is right at the location 9 of your logical memory. It can be. Okay, others are not valid in the sense they are not present in the main memory, but they are present on the hard disk, in the disk, right? They are present. You have to do a swap in operation to read it. Okay, all right. Okay, now okay, let's continue this part using the physical memory. Let's look at the physical memory. Physical memory will contain the some of the other parts which has not been shown here. So let's write the physical. So this is the physical memory, and the last part is the disk. Okay, now again we know that physical memory will have its own addressing. Okay, maybe the address corresponding to them will be 0, 1, 2. Okay, so when it says 4, right, it's actually, this part is called as a frame. This can actually contain where is it located in the physical memory. So for example 4, right, maybe the first one is A, but A, it says that it is present at 4, so the 4 will be like that's what is the usage of page table to identify where is it located, and the address can also be present over here. So we are right now we are using this address, so 4 is A. So the second one, if you see the logical memory, the 2 corresponds to C, and in the page table it is located at 6. Okay, so at physical address number 6 will be C, right? This is what is the physical memory, right? Then you can see that at 9 you have the fifth one, that is F. Okay, so at ninth location it should be F. All right, other space you see that it's not shown, there is nothing, it looks like, right, they are empty. But when you come to the physical memory location, let's write the physical, the disk, how the disk is getting stored. Okay, so how the disk is being shown here is, let's write in this way. All right, so first, second, let me write only 3 values here. So A, B, C, D, E, F, G, H, I, and so on. Okay, so we can fill it up in this fashion. Okay,
That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.